Hello everyone, this is Dr. Young, and I am going to take a stab and make a short video covering kind of what is science and the scientific method. We could talk about this for hours and hours and hours, and hopefully you guys do have some great questions for me in the future, but here's kind of like an overview and an introduction to these ideas. So when people first think of science, when I talk to people on the street or members of my family who aren't necessarily in science, they always think that science is like just a bunch of facts. Like if you are a scientist, you just spend all your time in a library and you're just memorizing tables of information. Um, and that's not what science is at all. Science is not knowing a lot of facts. It's a way of thinking and it's an approach to gaining new knowledge, right? So this is definition I like here. It's kind of the closest I think to a good definition of what science is, right? It's just this systematic approach to organize and to build knowledge, right? It's how we learn new things, true things, as opposed to false things. And the idea is that this way of thinking, this approach, is supposed to generate testable explanations, and it's going to help us build predictive models of the world. How does the world work? And by testable explanations, I mean like science is not going to predict, for example, if I looked at my glass of water on my desk and I leave it out for a week, not that that's ever happened, and I notice that the water goes down slightly every day, right? I might come up with an explanation that says that there are little frogs that come in at night and take little tiny sips of my water, and that's why the water goes down. But they're not like any frog. They are actually magical frogs from the fairy realm that are invisible, don't give off heat, don't leave footprints, and are like kind of almost ghosty. So you just can't really like see them or touch them or smell them or anything. That would be an example of an explanation of why my water is slowly leaving my glass, is slowly going down. But it's not a testable explanation because there's nothing there, right? I can't test to see if these weird little fairy frogs are actually doing it, right? Because part of the explanation is that they are untestable, that I can't see them or touch them, or I can't do anything to prove that they're or not, right? So I'm not talking about like any explanation that you can just come up with. I'm talking about testable explanations, things that you can actually determine if they're true or false. And then as far as building predictive models of the world, right, this is how we get airplanes to fly. This is how we know the sun's going to come up tomorrow. All of these sorts of things that we know about the world. And I need to say just a couple things about pseudoscience. I think it kind of helps emphasize what science is to see what science isn't. Unfortunately, these days we're seeing a lot more pseudoscience, pseudo meaning fake or false. Pseudoscience, so false science. We're seeing more and more of it in the media. One big difference between science and pseudoscience is that science tends to, we follow the evidence, right? We build theories and our understanding based on the evidence that we see. Pseudoscience starts with that flip. Oftentimes pseudoscientists start with a theory that they want to believe is true and then look for the evidence that supports that. And a great example is the flat earther movement stuff, where people are like, the earth is flat. I need to find ways to prove that it's flat. That is the opposite of science. We work the other way around. We look at the world around us and then we decide, oh, is the world flat or is it roughly a sphere? Another big difference between science and pseudoscience is that science embraces criticism. We welcome criticism. We need criticism, and by criticism, we don't mean like, "Hey, I think your thoughts on speciation are dumb," right? We mean like criticism, like, "Oh, actually, you said this, but I noticed that in this case, it doesn't seem to work that way. I think you should revisit that idea, or maybe you should take this into consideration, or constructive criticism or reasons to be critical. Critical just means that you're kind of skeptical about something. It doesn't mean you're being mean. Pseudoscience is very hostile to criticism, right? Usually, if you say that you try to challenge someone's pseudoscience, they don't take it well. They accuse you of being part of like the deep state or the man, or you're secretly working for another company. They're very hostile to criticism, and this also spawns a lot of conspiracy theories. Right, where if you challenge them in any way, it's like you're like, for example, homeopathy, right? If you challenge someone with homeopathy and you talk about, well, there's actually none of that compound in the solution that you're making anymore, and shaking it shouldn't make a difference. They're like, so what, do you work for Pfizer? Do you work for Merck? Like, you work for Big Pharma? Like that sort of reaction, right? If anyone accuses you of being part of something, nefarious, probably they're doing pseudoscience, not science. Science also tends to be really like conservative and tentative with their results, whereas pseudoscience tends to be very grandiose. So, like, a difference would be that with like the coronavirus, a reporter might ask a scientist, "Hey, will wearing masks stop the coronavirus?" And that scientist is probably going to say, we've definitely found that wearing masks lowers the transmission of coronavirus," because they're trying to be right, because they know that it's not going to completely eradicate the coronavirus. They just know that it's going to help a lot, and they're being conservative about that, right? They're saying like, yeah, no, studies have shown that it greatly reduces the transmission of coronavirus. Whereas a pseudoscientist would say like, yeah, wear this mask, 100% gonna stop coronavirus, and it's also gonna like detox your chi or something like that, right? They'll just go way off on a tangent and like promise way more than they can deliver, like the colloidal silver stuff going around, things like that. I'm not going to go through all of these. I just want to point out like one or two more. Like one, scientists do engage with their peers in the community. One of the great things about science, right, is that it is open to anybody. Anybody can become a scientist, and anybody can test anything that any scientist claims, right? There's nothing that like only like Sandra down in Minnesota can prove, and no one else can. Anyone can prove Sandra's experiments right or wrong. Anyone can just go do it exactly what she did, and then you'll get the same results. That's how science works. There is no lone wolf. I mean, I think on the pseudoscience side, right, they say lone mavericks or lone wolves working in isolation. They tend to be like, the one guy in his basement who discovers cold fusion, or the person who like develops the brand new cure for the coronavirus made out of a proprietary blend of herbs and minerals, but they won't tell you what it is, and only they know it, and they won't let anyone else examine it. They won't let other scientists like test it. Big differences between science and pseudoscience. So I hope that gives you a better idea of kind of what science is and what it's not. Now, the scientific method you've probably learned about multiple times throughout your just educational career here, but I'll just put it down here in simple terms and we'll kind of expand on what this means. Before I do any of these, I just want to say that the scientific method is something everybody does all of the time. It's how you inform the world around you. I have two small kids. I see them do the scientific method every day, just every day with like, I look at this stick. Is this stick delicious? Stick it in my mouth. It is delicious. Keep eating it. Oh, Dad doesn't want me to. Dad takes it away. That makes Dad mad. Well, what about this stick? No, Dad's upset again. Does Dad not like any sticks? Well, let's pick up another stick. Oh, nope, Dad doesn't like me to eat any sticks, right? They're gathering data to help form their model of the world, right, is the idea. So the scientific method, step one, you got to make some observation about the world. You're like, that's funny. Like that tree's growing, it's kind of weird that all plants kind of grow up towards the sun. That's interesting. Or, that's weird that like, that oil is always floating on top of the water, or whatever it is. Or I'm picking fairly simple things off the bat. So you make an observation and you form this testable hypothesis, right? Let's say like, oh, well, I think that, plants probably grow up because they're growing up to the sun or the light or something like that. And so then you want to design an experiment to test that. Like, well, maybe I'll, grow these plants, but I'll make it super dark and I'll put the light in like a funny place. Like I'll make the light go downwards or to the left or the right. So you want to design an experiment. And then next you need to actually perform that experiment. I separate these out, the design of an experiment versus performing the experiment, because sometimes designing an experiment is easier than performing it. And a really good example of that is you may have heard of those particle colliders. The Large Hadron Collider, for example, is the large one over in Europe. And you may have heard of the Higgs boson. Maybe you have, maybe you haven't. Higgs won the Nobel Prize in physics a couple years ago. And what was cool about Higgs is he came up with this theory for the thing called there is a boson, he predicted, that is what gives particles mass. And I'm not going to go into a whole thing about particle physics, one, because I don't understand it, and two, because it's complicated. But basically, right, all these particles that make up our matter in the world and light and all this sort of stuff, they're made up of even smaller particles that give them certain attributes, like being a positive charge or negative charge, or having mass or not having mass, or And so people didn't really know why things had mass until this guy Higgs came along and said, "Oh no, I think it's this boson here. I think there's this boson that provides a mass attribute to other particles." And he's like, "Here's what we need to do to find it. If you run this experiment, we smash these things together in this size collider. Here's what we should see from a bunch of the runs of this experiment." The problem was when he proposed this experiment, there were no colliders big enough to do it. He just couldn't. He wasn't able to perform that experiment because the technology didn't exist yet. There was just no piece of equipment to run that experiment. So it was a big difference, right, between designing the experiment. He had the design. He just couldn't perform the experiment because we didn't know how. It turns out that they did run that, just to finish the story, it turns out they did run that experiment. They did find the Higgs boson because there's a little blip in a line. And that's why he won the Nobel Prize, is because it took like 20 or 30 years later, they were able to finally build this collider that was big enough to test it. Turns out that he was right. They found a bunch of evidence to support that. And now we have a new particle, the Higgs boson. Anyways, you got to design an experiment, perform an experiment, then you got to collect and analyze that data, see if your experiment worked or not, and then you either accept your original hypothesis or you reject your original hypothesis, right? If you did the thing with the light and you move the light around in this container, and all of a sudden it seems like the plants like totally ignore the direction of the light, they just grow whichever way they want, then you'd have to reject your hypothesis that plants grow towards light. And you have to start thinking about, well, maybe they just go opposite of gravity, or maybe they just always go 90 degrees to the soil level, or, you come up with some other hypothesis, design more experiments, test those too. Now, I made the claim earlier that everyone does science, whether they realize it or not, formally or informally. So like, for example, I love this example. Let's say you wake up and your cell phone screen is black, and you want it to go, check the president's Twitter or, Facebook or something like that. That would be your observation, right? Boom, right off the bat, you made an observation about the world. And so you might think to yourself, oh, well, my phone must be off. That's why the screen is black, right? That's your hypothesis. You've got this theory that explains your observation. And I shouldn't say theory. I don't mean formal theory. I just mean like you have a guess. You're providing an explanation for your observation. And so you think, well, okay, well, maybe if it's off, right, I can just hold down the power button and turn it on, right? That's your developing an experiment, right? I'm going to test to see if it's on or off by, I could just push the power button. So this is design an experiment. And so you do, right? You perform the experiment. You hold down the power button for a few seconds. So perform experiment. And then you see that nothing happens, right? This is your results. This is you interpreting your results. And then, you start freaking out and the world is over. But you just basically did the steps, right? Like this would be the first thing you did. It would take you about 10 seconds, even in the morning, for you to just go through these. But this is the scientific process. Now, you could just freak out and that just be the end. But probably what you're going to do, right, is you're going to do that iterative process. I didn't mention it in the last slide, but the idea is that you're probably not going to freak out yet. You're going to come up with a new hypothesis, right? And then you're going to design a new experiment, test that, and see if it turns on. And then if that doesn't work, you're going to develop a new one, right? Because our cell phones are so important to us. You're going to try more than one thing. So maybe you think, right, okay, so maybe it's not off. Maybe my battery is dead, right? So maybe it just went dead. Maybe you forgot to plug it in or something like that. So you think, oh, well, I'll just plug it in and find out. Right? That would be designing your experiment again. You run your experiment by grabbing the cord, go in and plug it in. And now this time the charging symbol shows up and you take a sigh of relief and you're like, okay, phew, it was just dead. My cell phone is fine. And so then you are done, right? You had your observation of the screen was black, and now you know why. It was because the battery was dead. You just needed to recharge it. And if that didn't work, right, maybe you'd be like, oh shit, well maybe my charger's not working, or maybe my outlet is off, or maybe you'd come up with all these other explanations until you figured out what the problem was. And that's the scientific method. That's all it is, right? And so we just do this in more formal ways with other things that we're less familiar with, and that's what freaks people out, and we call it science. Now, the difference between a law and a theory, just real quick here. Some people mix these up. A law just describes a very predictable phenomenon. So, like, there's like a law of gravity, for example, law of aerodynamics. Those describe how aerodynamics work, and they describe how gravity works. There's an equation, for example, for the law of gravity. Let me just put that. Just as an example, there's a law of gravity. Right, so they explain how the natural world acts around us. Oftentimes, these laws are mathematical laws. Like you can say, like, the force is mgh, and there's all these variables and stuff. We don't have to get into that right now, but they just describe what happens. Now, theories are a little different in that they explain how that phenomenon works. And these explanations, they have to be supported by a huge amount of data. Laws are also supported by a huge amount of data, experimental data, but theories explain how the phenomenon works. So to stick with my gravity example, in my gravity example, we are not 100% sure how gravity works. We can't really explain it too well. We have some ideas of how gravity works, but there's this whole like relativity stuff, and why is gravity so weak if we can unify all the other forces, and like are we living on a brain of multiple dimensions? I mean, we don't have a great explanation on how gravity works, but we know that it works, and we know that it's predictable. So we're not 100% not 100% sure how gravity works. It doesn't mean that gravity doesn't work. It just means that we don't know how it works, right? No one's going to get into a plane and be concerned that we're not exactly sure how gravity works. We know how it works. We can fly people around in airplanes. We can go to the moon. We know, you've probably thrown a ball. You're not going to fly off of the Earth all of a sudden for no reason. We know that gravity works. We're just not 100% sure how gravity works. So theories are when you do gain a bunch of information and you do know how it works. Like we have something called the atomic theory, which we'll talk about soon, which is supported by an enormous amount of information that we've collected over many decades, centuries really, but most recently decades, of data that supports what an atom is, right? We think we know what an atom is because we have tons and tons and tons and tons and tons of data, and they all support the same idea. So that's going to be our little primer. I'm going to stop there. But what science is, kind of what pseudoscience is, the scientific method, and a little bit here about the difference between a law and a theory. Laws are observational. They describe things. Theories describe how something works. Both of these need to be supported by a very large amount of data. So study up. Good luck.